Hello everybody, this video is going to go over how we name acids and bases. We are also going to talk a little bit about how water self-ionizes and how that relates to our acid-base chapter. Before I start, I want to remind everybody that nomenclature topics are always tough because there's always lots of rules, there's lots of exceptions, there's lots of different styles of how we name things depending on what branch of science and chemistry you're in. So there will be things you just have to memorize, there will be rules that you just have to learn to follow. Realize if you Google something, you may not come up with the answer that we are looking for based on what we are teaching you. So if you remember from first semester, some people struggled with naming stuff, and part of it is that it takes practice. You gotta be willing to do the practice. Flashcards are great for nomenclature. You can find lots of worksheets online if you just search for things like acid-base nomenclature practice. So just expose yourself to as many practice problems as you need personally so that you can get good at it. So the first type of thing we're going to look at are what we call binary acids. They have a hydrogen and then something else that's very electronegative. When we name these, you're going to begin the name with hydro. That's your prefix. Then you're going to add the root of your electronegative element. At the end, you're going to change the ending to be ic, I-C, and then you end it by adding the word acid to the end. So let's look at these examples. Hydrobromic acid, not bromine, bromic. Hydrochloric acid, not hydrochlorine, it's hydrochloric. Hydroiodic acid. Just like in the beginning of the year when we were doing regular nomenclature and you had to learn the patterns of where you drop your endings and you would change the ending. Remember when we were learning how to name things like ionic substances? This is the same idea. You take the root of one thing and you replace the ending of it. It takes a little practice to hear the rhythm, but if you say them out loud, it will really help you as well. Hydrobromic, hydrochloric, hydroiodic, right? Hydrofluoric. So it can kind of get you that patterning if you say them out loud. Next, we're going to look at what we call oxyacids. An oxyacid is a type of acid that has oxygen inside of it. It will change how we name things a little bit. You're going to begin with the root of whatever your ion is. You're not starting with hydro this time, okay? You may have some prefixes like per or hypo that you have to work with. And the endings are going to be things like ic or us. The way we get these prefixes and these various endings is based on a pattern that I'll show you on the next slide. You'll then, just like before, end the name by adding the word acid. So let's look at how we figure out whether or not you have to have one of these prefixes and which one, and whether or not you have to have one of these endings, which one of these to use. It depends on how many oxygens the anion comes with. The anions are going to have kind of the same foundation, and then you're going to have more or fewer oxygens. If the name of your anion ends with the ending ate, like phosphate, chlorate, sulfate, you're going to replace the ending with ic. If your anion ends with "ite," you're going to change the ending to "us," O-U-S. If your anion has an extra oxygen than your 8, then it's going to start with "per." If you have less oxygens than your "ite," you're going to start with "hypo." So you kind of have 8 as what you begin with. If you go above that in oxygens, you add a prefix. If you have "ite" and you go below that in oxygens, you add a prefix. So let me show you on the next slide. I'll use chlorate as my example. We start with chlorate. If I add a hydrogen to this, it would be chloric acid. If I add an extra oxygen, now it's perchloric acid. Per tells me I have an extra oxygen. What if this time, instead of the 8 version of the ion, I had the "ite" version? So instead of 3 oxygens, I have 2. Well, if you have the "ite," you're not going to end like this. You're going to change the ending to "us." Chlorous acid. What if I took another oxygen away? What if I had one less than the "ite"? Well, then it would be hypochlorous acid. Most people find it easiest to start with the 8. We use those ions the most typically. Phosphate, chlorate, sulfate. So then what you would do is you would go up from there and you'd go down from there. If you don't know your common ions and you're not good about the difference between 8 and "ite," this is going to be tough. It might be good to go back and refresh your memory on your common ions. All right. Another thing that's hard is sometimes we mess with the pattern of the naming a little bit to make it sound better. If you remember when we were naming ionic compounds and we had double vowels, we sometimes messed with the naming. We didn't want to have double vowels bumping into each other, so we do a similar thing here. We say phosphoric acid, not phosphic acid. Phosphic is like awkward to say. We say phosphoric acid. We also say sulfuric acid. We don't say sulfic acid. One of the reasons why this is one of the few chapters that flashcards are good is because you do just have to memorize some of those weird things like this. Next thing we have to remember is that these are still ionic compounds in a way, right? We still have to make sure that they're going to have a neutral formula. So you're going to want to cross over to figure out how many hydrogens these each have. So if you have carbonate and you're trying to figure out carbonic acid, well, if a carbonate is a 2-, I will need 2 hydrogens to make carbonic acid neutral. The other thing is names get weird fast, right? Focus on your patterns, memorize the weird ones, do a bunch of practice. That's all we can do. There are probably out there on the internet tricks and mnemonics and things, cartoon pictures, weird things to help you remember. Great. If you find something awesome, send it my way. right? I'm always happy to add, whatever might be helpful to people. Let's do some practice. What is the name of that acid? Well, it's binary, right? It's simple, so it's going to start with hydro. This is fluorine. I'm going to drop the ending and replace it with ic, and then I'm going to add the word acid. Hydrofluoric acid. What about this one? Well, binary, hydro, this is sulfur. Remember, change the ending to ic, but it sounds weird, so we mess with it a little bit to make it sound better. And then we're going to end it with acid. Hydrosulfuric acid. What about this one? This one is not binary. We have a polyatomic ion in here, so it is not going to start with the word hydro. I'm going to take my polyatomic and change the ending to ic. Because this is the nitrate ion, 8 is going to change into ic. This is nitric acid. Compare that to this one. This is not binary. There's a polyatomic. It's not going to start with hydro. This is nitrite. See how it has one fewer oxygen? That makes it the ite version. If it's the ion that ends in ite, we're going to change the ending to be us. Nitrous acid. What about this one? This one is also polyatomic ion. It's not binary. Does not start with hydro. This is sulfate. So I'm going to change the ending to ic. The 8 version turns into ic. Sulfuric acid. Sometimes people don't like that this one up here says hydrosulfuric acid, and they're like, okay, there's a hydrogen, makes sense. But down here, they're like, but this still has hydrogen, and this also has oxygens, and the names seem like they should be more different than each other. Well, it just is what it is, okay? The rules are what they are. Another thing that can be tough is there can be some more commonplace names. Sometimes the official acid name may not be what you see commonly used. No big deal. Some acids go by really old-fashioned names instead of more modern names. No big deal, right? Follow the pattern when you can, memorize things when you can't. All right, switching gears a bit, let's look at the difference between strong acids and bases versus weak. You gotta memorize the ones that are strong. Nobody wants to hear that, but you do. You gotta memorize it. What it means for them to be strong is that they're going to dissociate completely. They're going to break apart into their ions all the way. Hydrochloric acid is a strong acid, lots and lots of ions. These are the easy ones. These are the ones you want to have. These are the ones with simple pH calculations. We like strong acids and bases. The strong ones are the better ones. They make our life way easier. In this class, we are going to use 7 strong acids. You have these on your sheet from the very beginning of the school year. You do not need to write them all down right now unless you want to. You could reference your reference sheet if you'd rather. You got to be careful because so many of these ions are similar to each other, right? Some are strong, some are not. Nitric is strong, nitrous is not. Sulfuric acid is strong, hydrosulfuric is not. You gotta be very careful. If you look at those binary ones at the top, you should notice that fluorine is not part of them, are they? Hydrofluoric is not strong. It's weak. Doesn't mean it's not dangerous. Doesn't mean you want to pour it all over yourself, right? They're still dangerous chemicals if they're weak. It's just that, for our purposes and our calculations, they don't dissociate all the way. So just be careful. These ones are some oxyacids. Let's look at our 8 strong bases next. You will notice something about these strong bases. Are you noticing a pattern? Do you notice something about these? These are all alkali metals, aren't they? And they're all hydroxides too, aren't they? And down here you have a couple of the alkaline metals. Okay. Please believe me that I wouldn't ask you to memorize things if it wasn't important. Think about the analogy I always use of trying to write an essay in your English class. If you had to look up every word in the dictionary, you would never finish your essay, would you? You gotta memorize the strong acids and bases so that you have time to finish problems, okay? The strong and weak acids and bases behave differently. We do our calculations differently. If you don't recognize them as strong or weak, you're either going to run out of time or you're going to do things wrong, okay? All right, sometimes you may hear the term neutralization reaction. A neutralization reaction is what happens when you mix a strong acid and a strong base. They neutralize. You're going to get water as a product and you're going to get a salt. Not necessarily table salt, not necessarily sodium chloride, but you will get a type of salt, an ionic salt. It's always the same pattern. If you take hydrochloric acid and sodium hydroxide, mix them together, you're going to get water and sodium chloride. You should notice this is a double replacement reaction, isn't it? Acid-base reactions are like a subset of double replacement. Here's another example. Sulfuric acid and potassium hydroxide. You get water and potassium sulfate. Potassium sulfate is a type of salt. Salt is a category. Salt is an ionic substance that you get from a neutralization reaction. If you mix a strong acid and a strong base, you get salt. These are both salts, okay? The pattern is always the same. That's what's kind of nice. We do a whole lesson on learning how salts behave when you dump them in water. So being able to recognize a salt and figure out what it came from is very important. You got to know those strong acids and bases to do that. All right, next I'm going to just kind of propose a question to you that sometimes people never stop to think about. They just accept it as fact and they never stop and wonder why. Why is the pH of pure water 7? Why is that the number we get? And it's because water itself dissociates. It self-ionizes. It's not a lot, but it does happen. There's an equilibrium happening here. Water is going to break apart and reform. Back and forth all the time. We get conjugate acid forming and conjugate base forming. It's not a lot, but it's just a little bit. If pH is measuring the concentration of our hydrogen ions, right? And we have this equilibrium happening, well, there is some acid present, isn't there? There are some hydrogen ions floating around. So we have this dissociation happening. So how would we find the concentrations? Because the concentrations are going to help us find our pH, right? So how do we find those concentrations of this? Well, we use our equilibrium expression. We're kind of right back to the equilibrium chapter, aren't we? We have to write a law of mass action. We have to write an equilibrium expression. We need a K value. So if we have this reaction, and I want to write a law of mass action, products are on top, reactants are on the bottom. But look, water is a liquid, so it doesn't participate in my law of mass action. It's not there. The K value for the ionization of water, we put a little subscript of a W. Kw is the K value, the equilibrium constant for the self-ionization of water. Remember, those liquids don't show up. Well, this right here should look pretty similar to something else you've seen in the earlier video. One of our pH calculations looked just like this, huh? Now, at 25 degrees, and only at 25, this only works at 25 because remember, K values change, concentrations change based on temperature. So only at 25 does this work. If you're not at 25, you need different numbers. If you are at 25 degrees, when water self-ionizes, both of them are going to have this concentration. When you plug that in, this is what you get for Kw. You should remember from one of your pH squares on our pH calculation lesson that the concentration of hydrogen ion times the concentration of hydroxide equals 1 times 10 to the minus 14. That equation came from the fact that water will self-ionize it. It breaks apart. So you can use this to solve for things, right? This, you should notice, looks just like your equation from our calculations. And if these are equal amounts, if your acid equals your base, what do we call that? We call that neutral. And if you were to plug 1 times 10 to the minus 7 into your pH calculation, negative log of this number is going to give you a 7, isn't it? That's why water has a pH of 7, and 7 is considered neutral. Okay. This is all just manipulations of the same numbers. We are just rearranging, solving for different pieces. They're all interconnected. Okay, they're not technically separate equations, are they? We're just doing weird manipulations of them. All right. So you can use your KW equation to help you do these calculations if you want. So if you're told what the concentration of your hydroxide is, and you know that in water your K value will end up 1 times 10 to the minus 14, you can plug in your hydroxide and figure out what the concentration of hydrogen must be in this scenario. And you find out it's 1 times 10 to the minus 11. Now you could plug that into a logarithm equation and figure out what your pH is, right? It's all just manipulating numbers. All right, the last couple slides are some links to other videos that I want you to know about. If we have time in class, we will often watch these together in the classroom. Otherwise, I'll probably ask you to watch them at home because I do find them helpful. There's a video on the dissociation of water. It's a great one. This is a little trick on how to memorize some of your strong and weak acids and bases. The only problem is that they missed two that we use a lot. So just be a little careful, but it's a cool little trick. And then a crash course video. That's really great. He does talk fast. Remember, you can use subtitles and you could even slow down the speed if he's too fast for you. But he does a great job. Great animations. And then this video down here is about something called buffers. And it talks about acid rain. And those are both things that you learn about in AP chemistry. So it's kind of a nice little sneak peek to a topic that you learn about in AP Chem. All right, everybody, that was it for this lesson. I hope that was helpful. Bye.